Hi, we're here to talk about migration and its effects on a population's genotypic and allelic frequencies. So what is migration and how does it affect populations? Migration is when a group of individuals from one separate population with different genetic frequencies moves to another population and intermates. Migration is a violation of what is called the Hardy-Weinberg equilibrium. There are various assumptions for the Hardy-Weinberg equilibrium. The first being infinitely large population, random mating, no selection, and no migration. And it's important to remember that migration is a clear violation of this. So how does migration affect genetic variation? Well, there's two ways that it can affect genetic variation, and that's either within populations or between populations. So say you have this population of brown squirrels at NC State, and you have this population of brown and gray squirrels in North Raleigh. So right now, there's not much genetic variation within the population at State, and there's quite a lot of variation within the population in North Raleigh, and between the two, there's a lot of variation. So say this one gray squirrel says, hey, I'm going to go to State, and it goes over to State. Now, within the population at State, there's more genetic variation, whereas within the population, and that's only within that population at State. Now, within only the population in North Raleigh, there's less variation because alleles left. There's less variation. And between the population, the variation has decreased because they have more similar allelic frequencies.
Now here's an example problem. So suppose there are 80 squirrels, visualized here with 8, on the NC State campus. Squirrels around the NC State campus mostly only have the brown color coat, whereas in the nearby neighborhood, the squirrels mostly only have a gray coat. The frequency of the big A allele on the NC State campus is 0.7. 20 squirrels, pictured here by 2, from the nearby neighborhood migrate to NC State. The frequency of the big A allele in the immigrants, being the nearby neighborhood, is 0.5.
There's one equation that you will use that will be helpful for solving migration equations, and that is to find P prime, which is the frequency of the allele that you're looking at after migration has occurred. Now P prime is equal to 1 minus M, which is the migration rate, times little p, which is the frequency in the non-migrating population, and it's that product plus M, the migration rate, times big P, which is the frequency of the allele in the migrating population. Now I'm just going to write out these variables one more time. So P prime, remember, is the allele frequency after migration. So that is what you're looking for. M is the migration rate. And this is usually given in the problem. Little p is the frequency of the allele in the non-migrating population. And it's important to keep little p and big P straight. And big P is the frequency of the allele in the migrating population.
Now here's an example problem. So suppose there are 80 squirrels, visualized here with 8, on the NC State campus. Squirrels around the NC State campus mostly only have the brown color coat, whereas in the nearby neighborhood, the squirrels mostly only have a gray coat. The frequency of the big A allele on the NC State campus is 0.7. 20 squirrels, pictured here by 2, from the nearby neighborhood migrate to NC State. The frequency of the big A allele in the immigrants, being the nearby neighborhood, is 0.5. Using the formula, we must find the different variables in the problem. Little p and big P are given to us within the problem. The frequency of the big A allele in the campus population is 0.7. This equals little p. The frequency of the big A allele in the migrating population is 0.5. This equals big P. Now, the only other variable we don't know is m. To figure this out, we must take the number of squirrels migrating into the population, which is 20, and divide it by how many squirrels will be in the population after migration occurs. So 80 squirrels are originally there, plus 20 are migrating in. So 20 divided by 100 equals 0.2. Now that we know what numbers to plug into the equation, we can solve for p prime. So it would be 1 minus 0.2 multiplied by 0.7 added to 0.2 multiplied by 0.5. Once all of this is worked out, it equals 0.66. This means the allelic frequency for big A equals 0.66. Once you have found the allelic frequency of the big A, finding the little a is easy. Since the frequencies of little a and big A should equal 1, we just have to do 1 minus 0.66 and get 0.34 for the allelic frequency of little a.
So after you find the allelic frequencies, the next step in this problem is finding the genotypic frequencies. One definition of a population is its genotypic frequency. This frequency gives an indication of the genotypes that are the most and least prevalent in a population. So at the beginning of the problem, before migration occurred, the most prevalent gene at the NCSU campus was brown, and in the nearby neighborhood, the most prevalent was gray. After migration of the 20 gray squirrels, that genotypic frequency is going to change. An important equation that you will use in finding genotypic frequencies is of the following. P squared, which will be your homozygous dominant, plus 2pq, which will be your heterozygous allele, plus q squared. You will use this in finding all of your math calculations for genotypic frequencies. The genotypic frequencies found here are after one generation. So as you learned before and calculated the new allelic frequencies for this new population, A equals 0.66 and little a equals 0.34. These will be vital in finding our genotypic frequencies. I will describe to you how to individually get the values of the homozygous dominant, heterozygous, and homozygous recessive frequencies. Then I will show you a common way to check your answer. In this case, we would use the P frequency, which is our top one right here. We would then square this value to get the genotypic value of the homozygous dominant. This will look like this. This value will give us 0.4356. So the genotypic frequency of the big A gene in the new population is equal to 0.4356. Now that we know the new frequency of the big allele homozygous, we must find the heterozygous genotypic frequency. In this case, we will use both allelic frequencies because within our problem, it's 2pq. will be our heterozygous genotypic frequency. So it will look like this. 2 times 0.66 times our Q value of 0.34. This will give us a value of 0.4488. So overall, the genotypic value of the heterozygous genotype is 0.448. The reason that you use both allelic frequencies in this case is because one is trying to use the big allele and then a small allele within the genotype. For the next frequency, we will find the frequency of the homozygous recessive genotype. In this case, we will only need to use Q. This can be solved by solving for Q squared. So to solve for this, we would use 0.34 squared, and this would give us 0.1156. This value right here is the new homozygous genotypic frequency for the new population after 1 generation. After solving for each genotype, overall we got a new genotypic frequency of 0.4356 big A plus 0.4488 big A little a plus 0.1156 little a little a. I will now explain a good way to check your answer and make sure that you got the correct genotypic frequency after 1 generation. First, you take both of your allelic frequencies and you plug them into the equation that we used to find our genotypic frequencies. So to check, plug in the numbers like this. 0.66, which is your p-value. You square that plus 2 times 0.66 times the q value of 0.34. Then you add this to q squared, which is 0.34 squared. This is a straight using the equation p squared plus 2pq plus q squared plus q squared. So to check this, this will equal 1. You should then solve for the equation, and if it equals 1, then you correctly solved for your genotypic frequency. And in this case, our genotypic frequency, all added in the equation, equals 1. So we completed the problem correctly. After viewing this video, we hope that you understand migration and some of population genetics. Overall, migration is when a group of individuals from one separate population with different genetic frequencies move to another population and intermates. Migration is a violation of Hardy-Weinberg equilibrium law. It is an extremely important topic in regards to genetics. This concept allows the prediction of genotypes for new populations of individuals and is essential for the genetics world. Thank you for watching.